methods for the Schrödinger equation in the semiclassical regime, which describes the quantum dynamics of nuclei in a molecule, for example. And in doing so, well, we learned a lot. And I want to present you one section that will appear in this work, which is about variational Gaussian approximations. And I present this, it's somehow the simplest approach, maybe not the most accurate, but the one with a very rich mathematical structure, and say, like if you want to solve Hamiltonian problems, it's good to understand the symplectic Euler method. When you want to solve Schrödinger equations in the with a semiclassical scaling, it's good to understand variational Gaussians. So take it in that sense. And well, here's the outline. I will first tell you about the Schrödinger equation in what is called the semiclassical regime, which is a particular singularly perturbed scaling. And this scaling makes it necessary to use particular methods which behave well with respect to the scaling parameter, and variational Gaussian wave packets is what I will describe here. We'll come to some of the properties, in particular also to the approximation properties, to the equations of motion that drive the parameters of these Gaussians, and then we'll come to the integration of these moving Gaussians by a splitting integrator. So what is the Schrödinger equation in the semiclassical regime? What you're looking for is the wave function, which is a function of positions and time. And the positions here, if you have 3 particles, if you have n particles in dimension 3, then you have 3n coordinates. So d would be 3 times the number of particles. And even if you have only a few particles, this becomes quite a high-dimensional problem. And there's a scaling parameter epsilon here. Which, if you're familiar with the Schrödinger equation, looks just like h bar. But h bar is a dimensional quantity, and we are considering here the case which physicists roughly say, let's go h bar to 0. But in atomic units, h bar is 1. So what's rather here of interest is a typical action parameter that's related to the a non-dimensional action that's typical for the scale of this problem. And in many situations, this action scale is rather small, and you end up with this small parameter epsilon here, which will cause problems and opportunities. And we're considering the initial value problem here, where we specify the initial wave function, and we want to solve this up to a fixed time of order 1, let's say. And contrast to, say, an electronic Schrödinger equation, we consider here the case of a smooth potential. And this kind of problems typically arises in the quantum dynamics of nuclei in a molecule. Well, first, if you think of a molecule, you have nuclei and electrons. So it's an even higher dimensional partial differential equation. Take a small molecule like carbon dioxide. It has 3 nuclei, 22 electrons. So the next 25 times 3 gives dimension 75 plus time. But there's one thing which at the same time creates problems, but allows for a reduced model with good approximation properties. Nuclei and electrons have very, very different masses. And now one can make model reduction ansatz where one assumes that, that for any fixed position of the nuclei, the electrons are in the ground state of the full of the Hamiltonian of the full Schrödinger system for both molecules and things. And if you make such a reduction, which is called the Born-Oppenheimer reduction, then you end up with a Schrödinger equation which has a smooth potential, or at least I think there are theoretical results that it is at least 4.5 times continuously say 4 times or 5 times continuously differentiable. So if we make that more simplify this, we don't care about the smoothness, exact smoothness property. Let's take it C infinity. And there's the small parameter epsilon here, which comes in through this. Well, that's what remains of this mass differences between electrons and nuclei, and epsilon square is the mass ratio of electrons and nuclei. So think of epsilon square as something like 10 to minus 4, and then epsilon would be on the order of 10 to minus 2. But there are other models where epsilon is much smaller.
And V is induced by the nuclei alone, the potential V.
V would be, in theory, it would be obtained by solving the electronic Schrödinger equation for fixed, the state, finding the ground state of the electronic Schrödinger equation for fixed nuclei. That would be V of X. And of course, chemists are using all kinds of approximations to that. So, but in fact, even for a small molecule like carbon dioxide, we have reduced it from a 75-dimensional to a 9-dimensional problem. Well, but carbon dioxide is a small one, and now that you have a way to reduce it to something, let's think of molecules which have something like 10 nuclei. So that's what we want to solve. And this is described by an equation of this type with a smooth potential and with this small parameter epsilon. And in other areas of physics, such scaled, such Schrödinger equations with such a scaling appear also, and even with much smaller values of epsilon. Okay. I see something here. Oh yeah. This is this delay that you were thinking here. So, well, that's the model we want to take. Now, what are the computational challenges? Of course, there's the high dimension. That's obvious. But there's more to it. There are also high oscillations. Typically, solutions are highly oscillatory, but they are localized in something that is on an interval of length square root of epsilon, and they may look something like that. But in here, so that would be the absolute value of the wave function. But in here you have high oscillations with a wavelength epsilon. And that, of course, makes this problem challenging, because high oscillations and high dimensions, they don't go well together. I mean, if you have high dimensions and smoothness, then you have sparse grids, you have efficient Monte Carlo sampling techniques or quasi-Monte Carlo, but high oscillation together with high dimension excludes grids. You cannot use full grids, evidently, but you also cannot use sparse grids, because this doesn't go well with this oscillatory behavior. So this looks like a battle lost. No, there is a rescue, and the rescue is there are some particular functions which describe the behavior. We start from some localized object, which we can typically well represent by one or a few Gaussians, and there are ways to do that. And so let's assume that our initial data is a Gaussian of this type, possibly with some oscillations in here. And then we want to evolve this in time in such a way that we, as an approximation to our complicated, highly oscillatory, high-dimensional wave function, we just evolve a complex Gaussian. And this will have amazing properties. By the way, I have so far not explained why this scaling is called semiclassical. We will see that this complex Gaussian, the position of it essentially follows a classical motion. Well, that's just the simplest but most basic method. It's the most basic method in the sense that it's the simplest method, but also the most fundamental method where most of the ideas can be seen in there. Instead of just one Gaussian, you can take a Gaussian times a polynomial, and you will get better approximation properties. Or instead of just one Gaussian, you can take several or even a continuum of Gaussians. And there are methods designed for that. But this will not in the talk today, but it will be in our Acta Numerica article. So what are these variational Gaussian wave packets? And why are they useful to move around? So think of something like that. We are here at time equals 0. We assume that our solution can be approximated, or that our initial value is a Gaussian, possibly with oscillations in between. So the Gaussians would be the envelope. And that would be at time equals 0. And then at later time, we still want to approximate it by a Gaussian, but this Gaussian might be wider, so it may spread out or also go together. And of course it may move. Say if this starts here at 0, then it may move with some velocity here. And we want to approximate our wave function by such a Gaussian. And why this makes sense should become clear in the course of this talk. But now, what are these complex Gaussians? Well, they will be of the following form. I haven't included time dependence at the moment, so one complex Gaussian at a fixed time will have this form. It is centered at a point Q. So Q would be the center of the Gaussian. And then, you have an exponential with a quadratic term here. Well, that's what makes a Gaussian. There's a scaling I over epsilon here. Because of the I require that I times C, C will be a complex width matrix. So C is complex but symmetric. Not Hermitian, but symmetric. And we require that it has positive definite imaginary part, and this is just to ensure that the absolute value behaves like a regular Gaussian. So this gives us this Gaussian profile of the absolute value. Here I have a linear term. There's again centered at Q, but there's another parameter here, P, and this has the physical meaning of the momentum. So mass times velocity. So the momentum parameter is here, and then there's a phase parameter, which is a complex phase zeta, and the imaginary part of this phase is fixed such that this Gaussian has L2 norm equal to 1. Recall for the Schrödinger equation, we always look for solutions which have norm 1. So we have now, we make this as an ansatz to our approximation. And we have these few parameters: the position, momentum, the width matrix, and the phase. And well, then if you consider the averages of the position operator, which is just multiplication with x, over such a Gaussian, then you get exactly the center. So Q is the average position. And if you take the quantum mechanical momentum operator, which is this minus I epsilon the gradient with respect to x, and take the average here, then you get the momentum parameter p. So this is the kind of objects with which I want to approximate our wave function. And the first thing to notice is that these complex Gaussians form a manifold. And manifolds have a tangent space. And this tangent space is easy to compute. Well, what do you have to do? You consider a path of Gaussians, and you differentiate this. And if you differentiate here, then you will get powers of x coming down. If you differentiate, and in total, you get a quadratic polynomial times the Gaussian itself. So the tangent space of this manifold of Gaussians at a particular Gaussian U is just the product of any quadratic polynomials, or up to quadratic polynomials up to degree 2, multiplied with a Gaussian. So that's our manifold, and it has this tangent space. And now let's come to variational Gaussians. And this now leads us to a very general principle how, from given a differential equation which is too large, and given an approximation manifold, how do we get an approximation, a reduced model which approximates our differential equation? So what we're looking for is now a path of Gaussians u of t, which should be an approximation to the exact wave function psi of t. And the principle which describes this goes back to Dirac in 1930. 1930 was only 4 years after the Schrödinger equation had been formulated, but it was immediately realized that the Schrödinger equation is a wonderful equation, but not very practical to deal with it directly. So already at that time, people like Dirac were looking for approximate models. And the Dirac-Frenkel time-dependent variational principle, given an approximation manifold, we're looking for an approximation to the u of t in this manifold by following condition, namely that the residual of the Schrödinger equation be orthogonal to the tangent space of the manifold at this u of t. So we determine the time derivative as that element in the tangent space, which is orthogonal to the residual of the Schrödinger equation. So, and this should hold for all elements in this tangent space. Well, in numerical analysis recognizes immediately this is just a Galerkin method. But it's not quite the usual Galerkin method, because the approximation space depends on the solution itself. So it's a type of nonlinear Galerkin method. And I presented this for the Gaussian manifold, but if you look to the chemist literature, almost all approximations that they construct, they are based on this variational principle So they choose an approximation manifold. They never call it such, but it is. And then use this Dirac-Frenkel time-dependent variational approximation principle, one would say, in numerical analysis.
Is this equivalent to restricting the action to M and then taking variations in M?
That's equivalent to that. Yeah. So you have to take the Dirac action that corresponds to a Schrödinger equation and reducing that. That's equivalent, indeed. Yes. But let me come to the next thing. There's even more to it. So this is our Dirac-Frenkel approximation. And you can write this as, well, here I've taken the I epsilon below, but here I can take it also again here. I can write it as I epsilon dtu is a projection onto the tangent space of HU. And this projection, which goes from L2 into our tangent space, can be given two fundamentally different interpretations, which here luckily coincide. Namely, if you take the real part, so, well, there's one thing. For a Gaussian manifold, it is a complex linear manifold, which means that if one element is in it I times, no, the tangent space is complex linear. This is not quite obvious from the definition of the Gaussians, but it's obvious from here. If this is a tangent space, I times this is also in it. This is clear. It's not so clear from the description of the Gaussian because this has real parameters. So this is a complex linear space, and therefore this condition is equivalent to taking just the real part of it, because if I have the real part, I take I times V and I get the imaginary part, or I can just take the imaginary part of it. Now if I take the real part, then this can be interpreted as the orthogonal projection with respect to the L2 inner product, which is defined by the real part of this. And with this interpretation will lead me to approximation properties. But I could also take the imaginary part here. And then I have the imaginary part of the inner product, and I multiply it with minus 2 epsilon for traditional reasons. And then this is a skew-symmetric form. It's a symplectic form. And then this is not an orthogonal projection, but a symplectic projection. And this has the important consequence that I automatically get a Hamiltonian system on this manifold. And one consequence, easy consequence of this is that I always have energy conservation. So I have two things at once. And let me just show a picture. I'll draw a picture, because this, I could almost take yours. But so here I have our manifold. At time t, I'm sitting at the current approximation u of t on the manifold. And then the question is, in which direction should I continue? So I need a velocity. Now, ideally, I would take u dot equals, so I would start from that point and solve the Schrödinger equation, and that would give me the vector field, which is 1 over I epsilon h u. That would be the vector field, but that would lead me out of my manifold. So what I do is I consider the tangent plane, or tangent space, in that point, and then I project this down here, take this orthogonal projection, which at the same time is a symplectic projection. So that's the picture behind it. And so what I have here then is this projection of 1 over I epsilon h u. And of course this projection depends on the tangent space, and the tangent space depends on our current approximation. And I insist on the importance of this picture. Oh, where is it? Ha! Well, now I wanted to show you a slide which shows the cover page of my book from 2008, which just has this picture in front of it. And if I put the picture on the front of my only book on quantum mechanics, you can believe that I have a high esteem of that picture. So, well, we now have this double interpretation as an orthogonal projection, which is simultaneously a symplectic projection. And this will be very useful. Now, let's come to a very special case, namely the case where the potential here is quadratic. Now, the Laplacian applied to you, if you complete the Laplacian of a Gaussian wave packet, you get the quadratic function multiplying the Gaussian wave packet, and so this is in the tangent space. And therefore, if I consider this projection here, this term is in the this kinetic term, which contains the Laplacian. This is already in the tangent space, so there's nothing to project to. And then there's the projection of the potential. Now, but if I assume that the potential is quadratic, then again this is in the tangent space, because our tangent space consists of quadratic polynomials times the Gaussian. And so this is also equal to Vu. So I have Pu, Vu equals Vu, and hence what I have then I epsilon dtu, according to this to our approximation that we chose. This is the projection of Hu, but here this and this are just H plus V, so this is again the Hamiltonian. So we see that in the case of a quadratic Hamiltonian, the Gaussians are exact solutions of the Schrödinger equation. And please also note the way how we proved this. We didn't do any calculations except computing the tangent space. We know that the tangent space consists of quadratic functions times the Gaussian. And so we have the remarkable property, which is at the basis of all the further development, that variational Gaussians solve the Schrödinger equation exactly in the case of a quadratic potential.
This is the usual computation for a Coulomb potential, right?
No, there are no Coulomb potentials here. Coulomb potential would appear in the electronic Schrödinger equation.
Yeah,
And I've done this Born-Oppenheimer approximation, which gives me smooth potential.
But you can verify just analytically these are exact solutions, right?
I would have to compute it, but I needn't compute anything. I just need to know what the tangent space is. This is the quadratic polynomials times the Gaussian. And if I have a quadratic polynomial, this projection just it's already in the tangent space. There's nothing to project to. And so this would be the equation for the motion of my Gaussian in this manifold. But since in the case of a quadratic potential, we see that Hu is in the tangent space. So the Laplacian is always in the tangent space. And if a potential is quadratic, this is also in the tangent space. And then this is a solution of the Schrödinger equation. That's all. Of course, you can compute it directly, but then you have to know the equations of motion for these Gaussians, to which I will come later. But this is a purely geometric argument. So Gaussians are exact for quadratic potentials.
How much of this statement is true for arbitrary approximation manifolds, and how much is specific to approximation by Gaussians?
No, this result this depends on the Gaussians, because here I used that the tangent space consists of quadratic functions times the Gaussian. So this is very specific to the Gaussian. The previous this picture is universal to all approximations that are used by quantum chemists. And also this property that you have simultaneously an orthogonal and a symplectic projection. Now let's look at conserved quantities. Well, I told you already, since it's a symplectic projection, we get a Hamiltonian system, and Hamiltonian systems conserve the energy. So that's the average of the over the Hamiltonian. That's the energy of the system. This is constant in time. That's energy conservation of a Hamiltonian system. But there's more to it. The norm, well, we start from a Gaussian of norm 1, and we would like to keep norm 1. I mean, this has to do with interpretation of u of x and t square as the density of a probability distribution. So this should be 1, and it should be 1 for all times, and it is. And if my system is translation invariant, then linear momentum is conserved. If the system is rotation invariant, then angular momentum is preserved. And for the Gaussians, the linear momentum and the angular momentum are exactly the linear and angular momentum of the corresponding classical system that corresponds to the parameters, to the position parameter q and the momentum parameter p. And they are preserved exactly in these cases. And these three, so the energy comes from the Hamiltonian structure, and this one has a simple proof. There's a general result. If I have an observable A, well, then its average is for the Schrödinger equation is conserved if it commutes with the Hamiltonian. That's how conserved quantities in quantum mechanics arise. And now we have this approximation. And if we have the property that A maps the manifold, maps every point in the manifold into its tangent space, then a one-line calculation shows that the average remains conserved along the variational principle. Now, and here for the norm, you just take the identity operator. So U is a Gaussian, which is a quadratic polynomial times a Gaussian, so it's in its own tangent space, and therefore the norm is conserved. And similarly, you can use this result for linear momentum and angular momentum if you have the appropriate symmetries. So we have an approximation which has nice properties. We have energy conservation, norm conservation, linear and angular momentum conservation. But I was somewhat loosely speaking of this as an approximation. In what sense this is an approximation to our wave function? Remember, we still have this high-dimensional problem with highly oscillatory solutions. So that's now the question. In which sense does our Gaussian approximate the exact wave function, and with which accuracy? And I'll give you two results, of which I will prove you the simple one, which I still find remarkable. So we start from a Gaussian which has width square root of epsilon and such an oscillatory behavior. And we assume that the width remains bounded by a constant times square root of epsilon over the time interval over which I consider it, and that there is a lower bound on the eigenvalues of the imaginary part of C of t, and this determines the width of the Gaussian. So the Gaussian should not spread out arbitrarily, because then it becomes meaningless. But then, as long as it remains localized of width square root of epsilon, it approximates the exact wave function in the L2 norm with something that is proportional to the square root of epsilon. Now that's a remarkable result. We have this high-dimensional, highly oscillatory wave function, and this is just approximated by a Gaussian. As epsilon goes to 0, we have convergence. Except that this is, in practice, unfortunately, not such a nice result, because for the nuclei, epsilon square would be 10 to minus 4. So epsilon would be 10 to minus 2. Epsilon, square root of epsilon then is 10 to minus 1, and then you have a constant in front of it, and not much is left. But still, I find this a very remarkable result, and I want to give you the proof also because the proof is very short. How much time do I have? When did it start? Oh no, then I don't give it, well, I give it the basic thing in the proof. It turns out that you can bound the L2 error by the integral over the distance of, it's an a posteriori error bound that you get. It's the distance in L2 of our approximation yeah, 1 over I epsilon HU to the tangent space at U. And then, well, dt prime, if you want. Yeah. Now, what is this distance? This distance, well, h consists of the Laplacian, but Laplacian u is in the tangent space. Then it consists of a quadratic part, which is also in the tangent space. So it's the cubic remainder. So here we have our localized Gaussian of width square root of epsilon, and then there's a cubic function like that. And so essentially you have to integrate over that. And well, if you then this distance here in the L2 sense turns out to be square root of epsilon. And this just comes from the cubic remainder in the Taylor expansion at the point where the Gaussian is located, Q. So here just you take the cubic remainder. And since this is something localized, here the cubic remainder is small, but the Gaussian is large, and what remains is of the size square root of epsilon. So that's the mechanism behind it. So in principle, this is an old result which for non-variational Gaussians where the position momentum parameters evolve according to the classical equations of motion, this was proved by Hagedorn. But there's a new result which actually came as a surprise to us and which has a more complicated proof. You might not be interested in the error in the norm, but the error in observables. So you take some observables, position, momentum, some potential energy, kinetic energy, whatever. So functions of P and Q, which satisfy some growth conditions, and then you take the average over that. And the average is always the scalar product of U with A times U. And then the averages are obtained to a, where did here is it. The averages are obtained with better accuracy of size epsilon. And that already is significant because in the Born-Oppenheim approximation that I gave you quite in the beginning, where we reduced the complete molecular system to just the system of the nuclei, there's also no of epsilon error in there. So maybe it would be nice to have something even smaller here, and this can be obtained with other methods. But in the observables, essentially we are at the same error of level as we obtain anyway from the Born-Oppenheim approximations right from the start. And this is a new result which doesn't seem to have appeared in the literature before. No, so far everything has been abstract. I didn't tell you how can one compute with these Gaussians. We have these parameters, but how do they even evolve in time? And for this we must go back to our approximation. So we take the projection to the tangent space of the Hamiltonian operator applied to our Gaussian. And well, this is the kinetic part is already in the tangent space, so it's just a question, what is this projection of the potential applied to the Gaussian? And this one can calculate explicitly. I mean, this, of course, it should be in the tangent space, so this must be a quadratic polynomial times u. And so we make an ansatz of this form, a constant term, a linear term in x minus q, and a quadratic term in x minus q. And after some calculations, we find that this is almost like a Taylor expansion. So here for A, you have the second, you have the Hessian, but not the point evaluation at the center Q, but the average of it. Similarly, here you have the average of the gradient in the linear part, and here you have the average of the potential, but there's an extra correction term, which is not intuitive. But it's this correction term which in particular ensures these conservation properties that we had before, conservation of the norm, conservation of the energy that comes through that. So, and once we have an explicit form for this projected potential term, it's not very difficult to derive equations of motion. And what one gets is equations of motion for the position parameter and the momentum parameter. And if you look at them, they look just like the classical equations of motion, except that instead of a point evaluation of the potential at the center of the Gaussian, I have an average of the Gaussian. For the phase, there are some terms which contain an epsilon, but the dominant term is this is just a Lagrangian, so zeta will be the action. So this looks very closely related to classical mechanics, and this too, but this does not. Not yet. And these equations go back to 1990 to Cosen and Karls, and I guess that Karls didn't get his Nobel Prize for this derivation, but still. Apparently it was also not an obstacle. Now one can find a different parametrization, and this goes back to Hagedorn, and I find it really amazing. We have this matrix C, which is complex symmetric with positive definite imaginary part. And there's the following characterization of such matrices. Any such matrix can be factorized as P times Q inverse with a symplectic matrix that is built up of the real and imaginary parts of the two factors. And moreover, the imaginary part of C, which determines the width of the Gaussian, is just QQ star, just the inverse of QQ star. The proof is not so complicated. It's elementary linear algebra. But there's much geometry behind the matrices, complex symmetric matrices with positive definite imaginary part. They form what is called the Siegel half space, and Möbius transforms on this half space, or generalized Möbius transforms on this half space, have been studied from a purely mathematical viewpoint by Siegel in the 1940s. And so this result could also be derived from Siegel's result, but there's a very elementary proof by basic linear algebra also to it. But it's a remarkable result. But now, well, you can factorize it, so what? So what comes next? If you factorize it in that way, you get equations of motion for Q and P, which are just the linearized classical equations of motion. That's also why this is called capital Q and capital P. And now this looks almost fully classical. And in fact, if you just put a one-point Hermite quadrature on each of these averages, you just get classical equations. you solve the classical equations of motion, the linearized classical equations of motion, and you have some small correction terms to the action. And this was in an amazing work by Hagedorn considered non-variational Gaussians where you have point evaluations everywhere, and came up with these equations, that the variational equations really have this nice structure. It doesn't exist in the literature. But Hagedorn really is to be credited for this nice parametrization of Gaussians, which is really remarkable. Now, you remember these approximation results. They were saying that as long as our Gaussian is well localized, we get reasonable approximation properties. But it may spread out. And what do we know? How fast can it spread out? I mean, if the Gaussian would spread out immediately, the previous approximation result would be quite meaningless. And now the Ehrenfest time is what in quantum mechanics is called that time scale over which the dynamics of the Schrödinger equation can be approximated by classical equations of by classical motion. And now let's come back. We have to look at the smallest eigenvalue of the imaginary part of C, and the width is then the square root of the smallest eigenvalue, or 1 over the square root of the smallest eigenvalue times square root of epsilon. So that's the width of our Gaussian. So this is then, since this inverse is QQ star, this is just the 2 norm of Q times square root of epsilon. But Q is propagated by classical dynamics up to terms of order epsilon. And so Q can only grow if the linearized classical dynamics grows, but the measure for this growth is the Lyapunov exponent. And so the classical Lyapunov exponent of the classical dynamics determines the spread out of the Gaussian wave packet, which is a remarkable result which you only get from this Hagedorn parametrization. I wouldn't see any other way to get this. And so if we have an integrable system, then we can go very far over very long times with our Gaussians, with just linear growth, error growth. Well, if you have a chaotic system, then there's exponential growth, and at some time, well, of course, when the cubic remains is such and my Gaussian is so flat, there's not much to be gained. Okay. So these are the equations of motion which we want to solve numerically in a decent way. In decent way, I mean preserving all the good properties. So that's where we are back to geometric numerical integration. And the method we have come up is a splitting method built on the variational formulation. So here once more is this Dirac-Frenkel approximation principle, this Galerkin method on the solution-dependent tangent space, with our Hamiltonian, which is built up of the kinetic energy operator, which is the Laplacian, or epsilon square scaled Laplacian, and the potential. And now I just do a Strang splitting here, where I first make a half step with the potential part of it, then a full step with the kinetic part of it, and then again a half step with the potential part of it. So far it doesn't seem as if we have gained much, because out of one differential equation I've made 3, which is not always an advantage, but here it is. Because it turns out that if you look then at the parametrizations, you get the following actual algorithm. So in the half step with the potential V, what you actually solve are the following equations. So like in the classical Sturmer-Lorentz method, the positions remain unchanged in this step. It's only the position and this position matrix which change. And these equations then are trivial to solve. they are all trivial. Of course, U still depends on P and Q, but P doesn't enter the average. And Q is constant, so I can solve this trivially. Just, well, these are constant terms here, and here's a constant matrix here, and this is also constant. So this is solved trivially, and well, here it's a little, yeah, this is also solved trivially. So this part is completely explicit and trivial to solve. And for the kinetic energy operator, it's the momentum which doesn't change. It's just the position which changes in a trivial way. And all of this equation then can be solved analytically. This makes some logarithm appear here. And so we can solve each of these steps explicitly, cheaply, and the only cost actually is in computing these averages. But if you don't care for too much accuracy, you just take the one-point averages and you have evaluate them at the classical positions. Now, since this is a composition of Hamiltonian flows, albeit non-canonical Hamiltonian flows, this is an explicit non-canonically symplectic integrator or Poisson integrator in these variables. Now let's look what happens in the limit epsilon going to 0. In the limit epsilon going to 0, you average over the needle. So it's just a point evaluation. And then the algorithm that I gave you for the positions Q and P just reduce to the classical Sturmer-Weyl integrator, which is the standard integrator for classical molecular dynamics, and which is the prototypical example of geometrical numerical integration. So which is so in the limit case epsilon going to 0, it goes to the best to something that is the gold standard in molecular dynamics, which of course is a nice asymptotic property. I told you previously that our time continuous Gaussians have nice conservation properties. Now what happens here? Now energy is not conserved exactly, but it remains second order accurate independently of with a constant independent of epsilon over time intervals that go far beyond this Ehrenfest time that I have you. So energy conservation holds much longer than the actual approximations properties hold. And the way to prove this is this by now classical tool of backward error analysis, where you interpret the result of the numerical integrator as the exact solution of a modified Hamiltonian integrator whose energy is conserved and whose energy then is O of tau square, second order close to the true Hamiltonian. So this is this classical backward error analysis argument for showing long time energy conservation. But one must be somewhat careful here to guarantee uniformity in epsilon, which is not quite obvious because the Poisson system still has a 1 over epsilon in the structure matrix in one place. Also, it doesn't help that one has non-canonically Hamiltonian PDE underlying to that, because there's no usable backward error analysis for that. So one must go back to the ODE case, use the Poisson structure, and then can derive this result. And again, by construction, norm, linear, and angular momentum are conserved exactly, because it's a composition of flows which have these properties. So it has the same essentially the same nice conservation properties as the continuous flow. And finally, what can we say about the error? So now we compare the full discretization with the time continuous Gaussian. approximation. Now in the parameters, position, momentum, and these other parameters, there's second order. This is almost immediate because the equations we solve behave well in epsilon. However, due to the 1 over epsilon in the exponential of our Gaussian, there's only a tau square over epsilon estimate in the L2 norm. But in the observables, we get again uniform second order, uniform in epsilon in suitable observables that depend on Q and P. And these error estimates, of course, hold on fixed bounded time intervals. Now, with this, I've come to my end, and I hope I could show you something of the fascination of these Gaussians, which really combine in a very nice way quantum mechanics with classical mechanics. Thank you.
So in practice, in practice, people integrate these things long beyond the Ehrenfest time.
I mean,
is that a fundamental limit?
I mean, of course, they observe when this spreads out, and at some point they stop. What, according to which criteria they stop? I think that depends from user to user.
So if you extend the method by putting in lots more basis functions, you can just go a little bit further, or?
No, the Ehrenfest time cannot be substantially increased. You get a better accuracy on fixed time intervals. For example, if you take a polynomial times a Gaussian, this would be this Hagedorn wave packet approach, then you can get to arbitrary powers in epsilon if you increase the degree of the polynomials. But the time scale is not changed by that. So you are essentially limited to this Ehrenfest time scale with this type of methods.
I had two questions. So for ionization,
excuse me, but this Ehrenfest time is somewhat longer than the typical time scale of the classical system. So these are physically reasonable times, but it's not used for long time dynamics.
So I suppose, for exactly that reason, you can't use it to study ionization, where the wave packets spreads out much more?
I mean, of course, if you have tunneling effects where you have one particle here and the other one going out there, then one Gaussian is not the right thing to do. Then you need strategies to build up several Gaussians and to split them, to reassemble them, and chemists have been quite inventive in doing this. But as I told you, think of this as something like the symplectic Euler, and then of course there are much more refined methods for particular needs.
I have another question. You have second mixed derivative of the potential also that you require in this scheme?
I need a Hessian of the potential. The Hessian of the potential, yeah. Please?
So, you started with a problem that have different time scales.
Yes.
And now,
different time and space scales, yeah. Uh-huh.
But you use the Gaussians and then you only have to deal with one time scale? Or I'm getting...
In the end, yes. For the parameters that I develop, there's only the long time scale. The epsilon has disappeared or has become a regular perturbation.
So in the end, if I wanted to solve this, I say, okay, I have my Gaussian wave packets. I have to guess somehow, or you will explain us how. Well, you have the U. You have to compute the tangent space, but the wave depends on the momentum, the position, and those you solve through the 4 last equations that you arrive in that. Is that what you do?
Well, this is our Gaussian. Of course, the Gaussian has the 1 over epsilon in the exponent,
Okay.
or I over epsilon. But what I solve for in the end is for the parameters Q, P, and I want to use this complex width matrix C, but I will use it in this factorized form for the, I will solve it for the P and the Q.
Okay, but if you don't have a quadratic potential, you will also have to do a projection on the tangent space. So at every time I solve.
No, yes and no, but the tangent space projection is already built in our equations of motion. So this is what comes out after this tangent space projection. These are the equations that need to be solved numerically.
Okay.
And you see there's no bad dependence on epsilon anymore. There's a regular perturbation with the epsilon, but that's it. I must also say, in these averages, the oscillatory part falls out. So these are averages over smooth Gaussians. That's for the practice. This is extremely important that the oscillatory part cancels out in taking these averages which are needed here. And then I can use. Then it's just sampling a Gaussian, not an oscillatory one, a classical Gaussian. And there are many ways to compute integrals. There I can use Gauss-Hermite quadrature in lower dimensions, or sampling a Gaussian distribution by Monte Carlo techniques. That's of course very well developed.
No more questions? So let's thank the speaker again.